Okay, so here's what we're going to try and conquer. We're going to start talking about force. This whole unit is all about forces. That's pretty much all we're talking about here. We will start that by talking about the difference between mass and weight. A lot of people think that these are kind of the same thing. Now they are related, but they're very, very different. And finally, understand and know Newton's first law of motion, inertia. How many of you have heard that word? That's because you guys learned this probably in like 8th grade. Okay, we are going to, of course, go a little deeper with it than that. All right, but you know something about this already. Okay, so let's start out by writing down the definition of force. Okay, yeah, a little Star Wars for you. That's for you, Mitch.
I thought so.
Okay. All right, a push or pull. That is kind of a loose definition. A better definition would be anything capable of producing acceleration. All right, so there's some blanks on your notes there for you to fill in with that. Okay, now we're gonna talk about probably 8 or 9 different forces by the time we're done. The first one we're gonna talk about is weight. Weight is a force. Okay, mass is not a force. Okay, what's the difference between these two? Here's some definitions to start with. Mass is the quantity of matter, or how much material is there. So this is a kilogram. It says 1 kg on it. All right? That means there are enough atoms of iron, of metal right here, to give us a kilogram of mass. Okay? This is also a kilogram of iron. It says 1,000 grams on there, so remember kilo means 1,000. All right? And this will give us a mass. We'll talk more about that in a second. Okay, now units, I said kilograms. Now notice that that is not the base unit. So you know your metric staircase pretty well by now. And for mass, grams is the base unit, and 3 steps up from that is kilograms. Now this is what we actually use. We don't use the base unit in physics. Okay, in physics we use the MKS system. What's that mean? What's M?
Mass.
Meters. K would stand for kilograms, and S is seconds. Okay, those are our standard units that we use, even though it's not the base unit. Okay, weight. Weight is different. It is the force on the matter. Alright, in other words, how strong gravity is pulling on the matter or the atoms. Okay, so we got a scale here. This scale, well, let's talk about units first. Okay, units for weight. What unit are we pretty familiar with all the time?
Pounds.
Pounds, right? Okay. Pounds is a unit for force. Alright, for weight. In physics, we use the Newton. Scientists are so conceited, always naming everything after themselves. Newtons.
How do you abbreviate?
You abbreviate it capital N. Okay, good question. So, yeah, in parentheses in your notes next to that, capital N. Okay, Connor?
So if weight is measured by force, so if you went to the top of Fort Tier and took a weight of a rock and then went down to like San Francisco and took a weight of the rock, would they be how different?
Okay, very nice. If we take a rock and we weigh it at different elevations, we are then further from the center of the earth, thus changing gravity, and it would weigh different amounts. Yeah, and you'll actually do a problem later that answers that very question. And I think I did it for gold. If we buy gold here and sell it here, okay, what's the weight difference? Can we make money that way? Okay, it's a little scam, a little physics scam. Okay, that's a good question. Yeah, it will change the weight. Not very much, okay, because that elevation is pretty small. All right, so here's a kilogram. So say this thing right here, and that's the mass. Now if we put it on a spring scale, all right, and I have one right here. So this has got a spring in it, and if we put this on here, it reads almost 10, okay? In fact, it reads 9.8, which is a magic number that you already know, right? Okay, so 1 kilogram weighs 9.8 newtons. All right, now what if we take this to the moon and bring the same spring scale? Then what'll happen? Okay, so here a kilogram weighs 9.8 newtons. That doesn't work everywhere. That's only on the surface of the Earth where gravity is rated at 9.8 for the acceleration due to gravity. Okay, so let's get off the Earth for a second. All right, let's talk about same exaggerated, not to scale, by the way. Okay, it's just this, but so you can see it blown up on the moon. Okay, the mass, is it still 1 kilogram? I have it on the screen, but if we take this up in a rocket, land on the moon, take it out, did I change how many atoms I have here?
No.
No, it's still the same amount of matter, so the mass is going to stay the same. But, check this out. If we put it on the spring scale, here we got 9.8. Here we would only get 1.6. Okay, little g for the moon we talked about earlier in the class is 1.6. So if you drop something, it'll accelerate at 1.6 meters per second squared. Okay, so weight changes based on where you are. Mass does not. Yep, Elaine?
So in physics, obviously we use newtons for weight, but then why? So normally we would take that 1 kilogram thing and say this weighs 1 kilogram, and like if we like stand on a scale like ourselves, then we say like, oh, that's this many pounds or whatever.
Right.
So like I don't know what I'm trying to ask. Like why isn't that 1 kilogram? Like I don't know. Like do you know?
Why isn't, well,
It's just a different unit, right?
this is just a different unit, or newtons?
Newtons.
Newtons, okay,
Different
yes.
unit.
Newtons is just a different unit of weight. In fact, there's a conversion from newtons to pounds. So we could get the weight of this in newtons and then convert it to pounds. Okay, and then on Earth too, 1 kilogram is actually 2.2 pounds. But that conversion only works on the surface of the Earth. You can't go weigh this on the moon, get the pounds, and then convert it using that same conversion. Okay? Because the moon's gravity is different. Alright, Sawyer?
If you have like one of those, whatever they're called, block of something.
Yeah, just
If one of those is like lead and one of them is aluminum, do they have the same mass?
Okay. If they are the same size, if I have the same size of lead and aluminum, they will not be 1 kilogram. Okay?
No.
Because of the density. But can I have a kilogram of lead versus steel? The lead, if I had a kilogram of lead in this hand, how would it look? Smaller, because it's more dense. If I had a kilogram of aluminum over here, how would it look compared to this?
Big.
It'd be bigger.
So on Earth, then you can tell which one has more mass by the weight, whichever one has more weight. If you're on Earth the whole time.
Yeah, that's right. Okay? Alright, Connor?
So then how do we attain the mass of like a person? Because isn't that always changing with like the amount of food and water you put in? So then how would we get that? Because we always measure our bodies by weight.
Yeah.
How do we do by mass?
Well, so if you drink a cup of water, yes, your weight is going to change. And your mass is going to change too, because you added mass to yourself. that water has mass. Okay? All right, good questions. Okay, so there's our weights. They are different. Mass is the same. Okay, now this thing right here, please do not ever, ever again call that a scale. It is not a scale. What is it?
A weight measurer.
A weight measurer. Actually, it doesn't measure weight.
Mass measure.
It measures mass, and what would we call it? A balance. It's a balance. Okay, this is a balance too. All right, we put something on this side and we put other stuff on this side, and it balances it. Okay, so if I want to do this and then figure out how much mass I have by balancing out, would this thing still work on the moon?
Yeah.
Yes, it would. Okay, and this would too. This is just called the triple beam balance. And we have those here too, but these sliders just move instead of putting something on the other side. Okay, these things would give the same reading for this on the moon. Okay, now this operates differently. If I take this to the moon, this has got a spring in it that is counteracting gravity. Okay, so this will give us different measurements. So what's this measure? Weight. All right, cool. Okay, so these would have springs inside here, we'd get different weights. All right, inertia. A couple blanks to fill in. It is an object's resistance to change. Okay, resistance to changes in motion. Okay, certain things resist change more than others. All right, so if we put this down here and highlight it, what's another way to say that in one word?
Acceleration.
Acceleration, good guys, yeah, okay. All right, an object's resistance to acceleration. So more inertia, more resistance. Okay, furthermore, these two words, how do they relate? Here's the deal. Mass is a measurement of inertia, and I think I put that in your notes somewhere. It's a blank too. Mass is a measurement of inertia, and its unit is kilograms. Okay, so when we're talking about kilograms, when we're talking about mass, that's how we measure inertia. Just like we use meters per second to measure speed or velocity. Okay, they're directly proportional. All right, so a couple demonstrations with this. Okay, for its size, this has got quite a bit of inertia, right?
Yeah.
Yeah. Okay. Cool. All right, so let's hang this up here. So if it's got some inertia, then it resists change. It resists. So what's it doing right now? It's just sitting there. It's not doing anything, okay? So what does it want to keep on doing? Just stay sitting there. All right, now I've got a string down here at the bottom. Okay, and I'm going to pull on it. This fishing line. All right, I'm going to pull down on this. What's going to break? Is it going to be the top string or the bottom string? Okay, let's have a vote. How many people think the top string?
Whoever you type it.
Okay, how many think the bottom string? Okay.
Wait, they're both fishing line, right?
They're both fishing line, they're the same pound test, and I tied the same knot. Okay? Alright, ready? Well, oh, fail. That was anti-fact. The moment of truth. Okay, ready? Ah! The bottom string broke. Okay, good job. Alright, now I tied another one on here. Okay, and watch this. Now the top string. Okay, what was the difference? It was slower. It was all about the speed. Okay, yeah, and force comes into play there. Okay, so the first time I gave the stick a quick snap. Okay, and when I did that, I didn't give this time to be able to accelerate because this has got a lot of mass. Alright, it likes to keep on doing what it's doing. But if I apply the force slowly and give this time to change what it's doing, then me plus this will break this string first, just like you guys thought for the most part. Does that make sense? Okay. Oh, look at this. Here's some more lazy stuff just sitting here. Okay, dishes, they got mass, right? So if they're just sitting here, what do they want to keep on doing? Just stay sitting there. Okay, now, do we trust physics?
No. Sometimes.
I'm scared. Oh my gosh.
Okay, I'm going to pull the sheet out from under the tablecloth.
Straight down.
Okay, and look, I even put this mug that's got my kids' pictures on it. Okay, that's how much I trust physics here. Okay, ready? I really hope this works. Okay. Okay, yeah, just walk out.
Drop the mic. Yeah.
Alright, so this stuff's got inertia. If I pulled the tablecloth really slow, then would the same result happen? No. Oh, you want to try that one? That would be fun. Okay? Then I'm going to make a huge mess because I gave the stuff time to change what it was doing. Okay? Alright, now the next one, you might kind of enjoy this. I'm going to put on the rally coat here, which is the tie-dyed lab jacket.
Need a picture color.
I don't care about the color. Okay, fine, I'll fix the color. Okay, I need you two to, you're my helpers on this one. Okay, so you guys come around here.
Oh. Yeah, friend.
Okay, so we're going to move this stuff. Okay, Angel, you get the hammer.
Okay.
Okay, alright, so you're going to lift this, you're going to set it on me. Just right on my chest.
I don't like this game.
Oh, I think it cracked my back. Okay, now Angel, just give it a swing. Like just a kind of a gentle one.
Oh, okay, like this? Okay.
Okay, now it's still a hammer, right? Okay, now you can do it a little harder.
Oh god, okay.
Don't miss.
It doesn't even hurt. Okay, alright, do it again.
I don't like the noise.
Okay, I felt it, but it didn't hurt. Why?
The big old thing.
Okay, now take this off of me. Alright, so that thing has got a lot of inertia. So even though you're using a hammerhead, it's not going to affect because there's so much mass right here. Alright? Okay, now if I didn't have that, and I just gave Angel the hammer, okay, then that would be really bad, right? Okay, we already know that would not work out. Okay, so a few videos here. There's another ninja physics teacher right there. Oh, let's take it up a notch.
Oh.
Oh.
Oh. Fake video.
There's no way.
No. No, this one's a fake video.
Oh my god.
No, that's a fake video.
Yeah.
It is.
Okay.
I don't believe it.
All right, now Mythbusters did 3 dispute this one, and I think there's actually a piece of glass. It goes dishes, glass, and then tablecloth. So I don't really think it's real, but still, even with the glass there, they were still able to do it. Okay, Mitchell?
Like the dishes at the very end of the table wouldn't have moved, but like the ones closer to the motorcycle would have. If
Okay, we're done.
it was like a real video, then the ones closer to the motorcycle would have had more time to react.
Okay.
Oh gosh, yes. I'm sure this is
This is definitely relevant.
I love him.
I know it defeats the point a little bit, but
Oh, I never.
didn't notice that? See, physics is everywhere.
Boom physics.
All right, and this is my favorite one.
Here's what you do. Just sneak up in front of them and then home. And they do the rest. Watch this. Oh.
Okay, which part of the tractor has the most inertia?
The top.
Okay, it's the engine right here in the front. Okay, now the wheels have inertia too, but they're easier to get going because they have less. So the wheels get going really fast and the engine can't keep up with that acceleration because it's more sluggish. It's got more inertia, so its only option is to rotate, which we'll talk about in another part of the class. Okay, two situations you have to understand very well. And they're pretty intuitive, okay? Check this out. There's a box sliding across some surface, and it's got a bowling ball in it. Okay, when that box stops, what's going to happen? Okay. Stops, and the ball keeps going, just like you would think. Okay? Now, this is crazy. The same thing actually happens in the animal kingdom. Okay? Zebras, they got their stripes, right? The stripe part of the zebra is actually a little bit more massive than the white part, the black stripes are. Okay, so if a zebra stops too fast, what happens is the rings can actually end up on the front, and if it stops fast enough, it can actually lose stripes. Isn't that crazy? Animal kingdom. Connor?
Wouldn't, if you pulled the ball go like the back first and then forward? Or?
Well, we'll do that one here in a second. Okay, no, that's not actually true. Okay, alright.
Oh, wow.
Not being serious here.
No way. It's
Okay, here's the other situation. What if this thing's at rest and the box starts moving? What's the bowling ball going to do?
Goes to the back.
Okay, what did it do? It just sat there. Okay? If we start this too fast for the bowling ball to catch up, it's just like the dishes. Okay? It's just going to hit the back. Now, once it hits the back, there's a force, and it's going to start moving. Okay? Now, this can also happen in the animal kingdom. Okay? A little bit closer to the home, to your home. You let your dog ride around in the back seat ever? Okay, what happens if you accelerate from a stop sign too fast? Which way do they go? This could happen. Okay? Wedged between the seat, right? Okay, you got scratch marks. All right, hopefully nobody drives like that. Okay, now I'm going to show you a short video here. Okay, and there's a bus sitting here, and there's people in it. It's stationary, and it gets hit by another bus. Now, I never show you guys videos like that because I think they're funny. Okay, car wrecks are definitely not funny, but the physics within them is really, really important, and hopefully this class makes you a better driver, seriously. Okay, so nobody dies or anything.
But it's even worse for those on the first bus, unaware of what's about to happen, and with no warning, 16 tons of metal plows right into them. Passengers tossed around like ragdoll.
Okay, so what really happened here?
They accelerated really
They didn't accelerate.
Okay,
Yes.
all right. What happened was actually this. Here's the passenger. Here's the bus. Okay, another bus hits this. The bus moves forward, but what do the passengers do? They actually stayed in the same place. So the bus slides forward, and it looks like the passengers got thrown to the back of the bus, but they didn't. They stayed in the same place because they have inertia.
But it
Oh.
That's unfortunate.
Now it's
He did not hook up his back straps.
Okay, so the truck hit, boat kept going, right? Unfortunate way to end a day at the lake, right? Okay, homework, all right? At dinner, when you're eating your alphabet soup with your family. Okay, alternative, if you're not an alphabet soup type of family, all right? You're going to replace this with a bowl of ice water. So a bowl like this, put some ice cubes in it, put some water, fill it up, and you have two things to show your family. Okay, number one, you're going to rotate the bowl pretty fast, like this. Okay, just spin it pretty fast. Okay, what's going to happen to the ice and the water? It's going to do that. It's going to stay there. You're not giving it time to respond. Okay? Then, spin it slowly. Okay? And you're going to give that mass time to respond to your forces there. Get it going pretty good, and then if you stop the bowl, what's going to happen? It's going to keep spinning. And your little brothers and sisters will think you are the coolest older brother or sister that ever lived. Okay, and you'll gain their respect forever, and then they'll take physics. Okay, more inertia stuff. Alright, let's say you're out working on a fence or something, you're nailing pickets on, or let's say you're camping and you're chopping firewood, or you have an axe and you're chopping firewood, something like that. Okay, have you ever had the head of the tool fall off?
Yeah.
Off the handle? Okay. Yeah, it's annoying. It keeps happening, right? Okay, so you're out there and you take the handle and you're doing that to get the handle back on there. And your Uncle Harry walks by, who's more wise and has more years than you, and says, "No, kid, you don't do it like that. You take your hammer and you just tap, tap, tap it on." Okay? You guys don't have an Uncle Harry? Wise beyond their years? Okay, that is actually true. This will work. Okay, and it probably won't come off again for a while. Okay? Now why is that? Okay, which part has more inertia? The top. Okay? So if you get this thing moving by dropping it, when this hits, what does this want to do? It wants to keep on moving. And so it does. And it keeps on moving a little bit, and it'll tighten right onto the handle. Okay, that's your MacGyver physics move of the day. Curtis?
It'll still do that even if you have it upside down and you're tapping on the bottom of the hammer.
And you're tapping on the bottom.
Yeah, like that.
And you're tapping on the...
No, the top. No.
Oh, and you're tapping here?
Yeah.
With like a sledge or something?
It would take a little while. Well, because you still got gravity pulling down on the head.
Okay, I'll have to try that out. That's cool. I like that. Double MacGyver move. Okay, so if I'm driving around in the summer and you're out working, I do not want to see you doing that. Okay? Alright? This is Newton's first law, that is not. Okay, so Newton's first law formally stated. Oh, I typed that out for you on your notes. So you don't have to copy this down. An object will continue its present state of motion, meaning a constant speed in a straight line, unless acted on by an outside force. Now for the Mr. Hicks remix of Newton's first law. Mass is lazy.
Mass is afraid of change, man.
I was not going to beatbox. Mass is lazy. Okay, so in other words, this massive thing right here, if it is just sitting there, what's it want to do? Keep sitting there. Okay? Now, here's the other part of Newton's first law that people forget. Let's say Miss Bowen gets mad at me and she throws that railroad track through both doors and it's coming at me. Okay, it's flying through here at constant velocity. What's it want to do? Keep going. And it's going to be very hard to stop. Okay, so it applies to moving things as well. Alright, for example, if you don't wear your seatbelt, here's an animation of what happens. The car stopped because of the brick wall, but there was no seatbelt to stop the person. Okay? The seatbelt, you can call it, when you get in the car with your friends, you should now say, put on your Newton's first law safety device. Okay? Try it out. Yeah, but they'll think you're so cool. Okay, now a seatbelt doesn't stop your head. We don't have headband seatbelts that go right here, because then we couldn't turn our head to see if other cars are coming. So we have airbags instead. It's the next best thing. Okay, here's an interesting video. This is like a racing boat. Check out what happens.
Don't they fly out of the back?
We're gonna face a hard one, a little slower this time. Okay. I got it. All right. Go. Go. Good?
Whoa! Ejected.
Whoops.
Okay, here's the path they were on. The red path is constant velocity in a straight line. Okay? Now they were on that path, and people are made mostly of water, okay, which has got a lot of mass. So they wanted to keep going. Now, not in their heads, okay, but physically, as far as physics is concerned, that mass wants to keep moving in a straight line, and that's what it did, okay? They didn't get thrown out of the boat, by the way. They just kept going in a straight line, and the boat diverged from them. They didn't get thrown out, okay? And so the boat was able to make that turn because it's dug into the water. Angel?
Is the thing that's coming out of the seat, does that connect to their helmet so the boat stops running?
Yeah, I think so. I heard there's like a little,
Like a treadmill.
there's like a little beep when they got ejected.
But nobody actually
Yeah.
does that.
And I think there's those
I
on
heard
jet
that.
skis.
Yeah.
Jet skis have a
Yeah,
little
yeah, the
tether.
bracelet thing.
Yep. Okay. Oh, I had a slow-mo of it.
That's better.
Oh, the slow-mo's not on me. Okay.
Okay.
All right. Something for you to think about. Okay, there's you.
Yes.
When you were a little kid. Can't tell if that's a boy or a girl,
That's
so
a girl.
it could be in you.
That's a
All right.
That's a good boy. It looks like a
Okay, just pretend it's you, all right? So you're on this airplane. The airplane is going 500 miles per hour in this direction. And you say, hey, Mom, can I get out of my seat and play around in the plane? And she's like, okay, sure, go ahead.
She's a great mom.
So you're out running around in the plane, messing around, and, oh, look, you found a ball. And you say to your mom, hey, Mom, can I throw the ball around on the airplane? She's like, okay, go ahead. All right? And so you start by just taking the ball and throwing it straight up. Okay, now you do that. Does the ball do A, this, okay, or some version of that, maybe not quite as pronounced. Maybe you throw it up and it just goes behind you a little bit. Okay, that's still A. A is behind you. Okay, or B, does it do this? and come right back down, and you catch it as if you were standing on the ground.
B.
Wait, A and B is the same?
A is it goes
I
behind
said
you.
D. B.
B is you catch it.
B.
Okay? Alright, the answer is B. It will not go behind you. Okay? It'll go up and come straight back down. Alright. Now why is that? We're going 500 miles an hour.
Because the ball's also going 500 miles per hour.
Okay, how fast are the seats going?
500.
How fast is the kid going? 500. How fast is the ball going?
500.
How fast is the air in the plane going?
500.
500 or 0?
0.
500 miles per hour. If it was going
Okay,
0, it'd be
here's
really,
the deal.
really windy.
All right, let's say you're going 500, but the air's going 0. Aren't you ripping through the air at 500? Meaning 500 mile per hour winds.
Yeah.
Okay, so that's not happening. So everything's going 500, except for the little air currents inside the plane from like the little air conditioners that spray viruses down on you while you're riding in the plane. Okay.
What are you
Exactly. Not having to pull a conversation. Okay, here's a tree. The Earth is rotating at about 1,000 miles per hour. Okay? See the bird in the tree right there? Well, it's there. Okay? Now, can a bird fly down here, get a worm, go back up, and the tree will still be there?
Yes.
Yeah, we all know that that can happen. Okay, but how can that happen if the Earth is going 1,000 miles per hour?
The bird's also going 1,000 miles
The
per hour.
bird's going 1,000, the worm's going 1,000, the air is even going 1,000, plus or minus 30 miles per hour for wind speed, right? Okay, that's Newton's first law. Do you have any questions? Connor?
So like in the plane, with the air being like inside there, so is that like the molecules are being like contained in the plane? That's
Yeah.
why-
If we roll windows down, some weird things happen. Okay, also, what if we throw the ball up and then the plane accelerates at the instant the ball gets thrown up? Then it lands behind us. Okay?
And then
Curtis?
Why are pilots like in jets affected by the different speeds that?
Well, when we're talking about Air Force pilots, we're talking about the acceleration on all the turns and stuff, not the constant velocity parts.
Okay.
Okay, and yeah, we'll get to some of that. All right.
So, say the plane is